Hi, thank you so much for joining me. In this video segment, I want to focus on using an equation that applies to all three of our state functions, our enthalpy and free energy, as well as our entropy. And that's what I call, for lack of a better term, the sum of equation. So what we're going to do is take the sum of values for products minus the sum of values for reactants, because a delta in chemistry is pretty much always final minus initial. There can be one exception, as some teachers teach it. All right, so what we're going to be using for enthalpy and free energy are enthalpy and free energy of formation. This is a specific definition of a type of synthesis, and it's got three requirements that must be met in order for it to be considered a formation reaction. The first is we are going to form 1 mole of a compound. So let's take, for example, down here I have CO2, and that would mean I would be forming 1 mole of CO2. Okay, and in this case it's CO2 gas. So that's one criterion, is that it has to be balanced, so there's a 1 in front. The second criterion is that it has to be from its elements. So in this case, I have carbon and I have oxygen. Okay, so those are the elements that make this up. And then we have our third criterion. They need to be in their natural state at standard ambient temperature and pressure. So for carbon, that's going to be solid graphite. For oxygen, that's going to be O2 gas. So that meets the three requirements for being a formation reaction. And now we would have to balance that, keeping in mind that that has to be a 1. So I'd have a 1 there, and then in this case there's a 1 for the O2. Let's try these next two, and then we'll talk about entropy. So I want to form aluminum oxide. That's a solid, and I want to form those. I need to form 1 mole from the elements. We want to make this from its elements, so aluminum. Aluminum is a solid at standard ambient temperature pressure, and oxygen, which is a diatomic gas at standard ambient temperature and pressure. And now we have to balance that. I have 2 aluminums. Let me get a different color so that shows up better for you. 2 aluminums. Now you notice here that I have 3 oxygens. So what we will do here is we will balance this with a fraction. It's not uncommon to see fractions for diatomics. It doesn't make conceptual sense really. How do we get 3 halves of an O2? But it does make sure we don't imply that we are violating the law of conservation of mass, for example. So that would be that one. Okay, and then I've got water liquid, so H2O liquid, and that's going to be from hydrogen, which hydrogen is a diatomic gas at standard ambient temperature and pressure, and oxygen, which is a gas. Okay, so I'd need 1 of the hydrogens and a half of the oxygens in order to fulfill all 3 requirements to make 1 mole. So all of these are 1s from their elements and their natural state at standard ambient temperature and pressure. Now, these values are compiled in, appendices of textbooks or online, as are the next one. For entropy, we're not using formation values. We're actually using what's called the absolute entropy of the substance. What is its absolute disorder, or how many microstates are there, or how much freedom of motion do the molecules have. Okay? Now the next thing is if I'm forming an element in its natural state, for the delta G and the delta H, those are 0. That is not true for S naught. So the S naught for elements, excuse me, is not equal to 0. The only time we really have an entropy of 0 is when we have a perfect crystal at absolute 0. Its positional entropy or absolute entropy would be 0. Now, another warning when you use these is to watch out for states of matter. So the synthesis, or excuse me, the formation reaction of liquid water is going to be a different value than it is for gaseous. And so you really need to pay close attention to states here. Okay? And then these are calculated per mole of the reaction. And I will show you that a little bit more when we get into the calculations for this. So until then, this is signing off.